my opinion, the most commonly overlooked component in industrial design, especially in the automation world, is probably the coupling. Very often people make the wrong selection simply because they're not aware of all the different types of couplings that exist, or in many cases, some of the couplings are designed with very specific features associated with them that solve very specific things in terms of either solving for misalignment, and there's various different types of misalignment. You have angular misalignment, you have lateral misalignment, of axial misalignment. All of those things are very, very important. Couplings also incorporate other design elements for different purposes. Dampening is another commonly overlooked kind of scenario. When you are in a situation where you have a lot of shock loading in a particular system, and you don't want that shock loading either to propagate forward or even propagate back into a motor, for example, a coupling that can compensate for that type of shock loading is very, very important. We'll have people contact us and say, hey, my machine's not performing the way it's supposed to perform. We can't hit the speeds that we want to hit, or we can't, or the machine is not as precise as it needs to be. The repeatability of the assembly action or something along those lines is not meeting specification. So typically what we have to do in those scenarios is do a little bit deeper dive in exactly what that design engineer is trying to accomplish. We'll see people put in, for instance, a solid coupling where an elastomer coupling might be a better scenario in terms of damping. We'll see people put in, for example, in line shafting, it's a very common mistake to put in a solid bar, for example, in the line shaft. And then very often when they set the device in motion, they will see kind of a cogging effect where the one side is not behaving exactly like the other side is supposed to behave. And that's typically because the shaft is winding up and unwinding, acts like a spring, if you will. One of the common misconceptions is that solid bar is more torsionally rigid in terms of design. And the reality is a tube is the most torsionally rigid. It's also lighter, you can go longer spans, and you can incorporate on either side of that tubing different types of connector designs, either a bellow or an elastomer. You can even put torque limiters in there. So, we have to take a look at exactly what that engineer is trying to do again, and then try to assess what's the best design option in terms of a coupling for them. One of the other types of component designs that's very often overlooked is a torque limiter. We have found many instances where a design engineer wants to incorporate a bellow coupling or an elastomer coupling or a line shaft or what have you. And then very often, let's say there's a jam on the load side and the whole system has to somehow disengage. If you don't have a torque limiter in line with that type of system, something's going to break. Either you break something on the load, you break something in the power transmission drive, or you cause other damage in the system. And a relatively cost-effective way to ensure against damage is to put in a torque limiter. And in our case, we have what are called ball detent torque limiters, which can react super fast. Very often in the control mechanism, a design engineer will, for instance, they'll notice a torque spike in the motor. And when they see a torque spike in the motor, that sends a signal to the controls to say, shut the system down, we've got a jam somewhere. But it takes time when those signals have to kind of progress through the control system. Ball detent acts much, much faster. It's almost instantaneous. And there's a variety of different types of designs of ball detent depending on what a customer, again, is trying to achieve. If they need to hold a load or if they need to hold positioning or what have you, there's different ways that we can set up a ball detent coupling. But again, that's a very overlooked component that most people should consider in our case if they're trying to protect their loads. Customer asks us, what's the best coupling that I should use, or which coupling should I choose? We'll ask a series of questions to kind of hone in on what's a better technology. I mean, here at DieQua, we have elastomer couplings, we have bellow couplings, we have line shafts, we have torque limiters, and the hub designs for each of those can also be a little bit differently depending on how that customer has to install the particular coupling in their design. So we'll run them through a whole series of questions to try to figure out what's going to be the most appropriate design. So in many cases, for instance, if precision alignment is necessary, in other words, there's an encoder on the motor and they're trying to hold very precise positioning, then you need something that's very torsionally rigid, so that from the motor all the way through to the load, you have the exact positioning that the encoder is seeing. The opposite of that is something that is not torsionally rigid, like an elastomer coupling, for instance. And in this case, we would try to identify whether that customer has any kind of shock loading associated with their application. So in that case, if there's shock loading, you want to protect the load going in either direction. We've had some interesting applications where you have shock loading taking place at the load, reflecting back into the motor and destroying bearings inside the motor. So either way, we need to understand what they're trying to do, and in that case, an elastomer type coupling would be most appropriate. And then also, how they want to try to design it. We have split hub couplings. In other words, the customer doesn't have the opportunity necessarily to shove it onto the shaft axially, so they need to come in from either the top or from the bottom. And so we'll have what's called a split hub type coupling, makes it much easier to attach it. There are things called shrink disc type couplings, which compress all the way around the perimeter of the shaft, which are, in our opinion, some of the best types of coupling connections because it distributes the load around the entire circumference of the shaft. And contrasting that, for example, with something like a keyed connection, where all the load is transmitted because of the shear forces associated with the key. So there's a lot of design variability that we can put into play when we're just trying to help a customer make a selection.